In problem 19, we need to find the Taylor series for the inverse tangent of x around x is equal to 0. So our inverse tangent of x, which I usually write as a-tan of x, which is arcus tangent of x, is a function whose derivative is known. When we differentiate this function, we obtain 1 over 1 plus x squared. Now this resembles a very famous Taylor series expansion which deals with the geometric series. For the geometric series, we have a function 1 over 1 minus x, which is a sum of a convergent geometric series. And this is 1 plus x squared plus x to the power of 3 plus x to the power of 4 and so on, and can be written down as an infinite sum of x to the power of n, where n goes from 0 to infinity. This is a geometric series. But in our case, there are two differences. Here we have minus, here we have plus. Another difference is that here we have power of 1, x to the power of 1, and here we have x to the power of 2. But this results in a simple substitution. 1 over 1 plus x squared will be similar to 1 over 1 minus x, except that the signs will alternate and we will have all the squared terms. So we'll have 1 minus x squared plus x to the power of 4 minus x to the power of 6 plus x to the power of 8, and so on and so forth. So we can write this down as a sum where n goes from 0 to infinity of minus 1 to the power of n times x to the power of 2n. Now, since the arctan of x, when we differentiate it, yields 1 over 1 plus x squared, it stands to reason that if we integrate 1 over 1 plus x squared dx, we will obtain the arcus tangent of x. So we will do this over here. We integrate this by dx. We integrate both the left side and the right side. When we integrate the left side, we will obtain our arcus tangent of x. And when we integrate the right side, we obtain constant c plus x minus x to the power of 3 over 3 plus x to the power of 5 over 5 minus x to the power of 7 over 7 plus x to the power of 9 over 9, and so on and so forth. And this can be written down as a constant c plus the sum, where n goes from 0 to infinity, of minus 1 to the power of n times 1 over 2n plus 1 times x to 2n plus 1. This can be obtained either by directly integrating this general term or by spotting the pattern in this series over here as we take a look at the series term by term, and we see that this is a general term. Since we know that here on the left side we have arctangent of x, and on the right side we have this sum plus constant c, the only thing that remains is to take care of the constant c. If we plug in x is equal to 0, then we obtain 0 is equal to c, because all of those terms in the sum disappear because x is 0, and all that remains on the right hand side is c, and all that remains on the left hand side is 0. And finally we have our answer. Arctangent of x is equal to this sum over here. If we want to write it down term by term, here it is, x minus x to the power of 3 over 3 plus x to the power of 5 over 5, and so on and so forth.